So let's see how the first tool is structured. Assume the case where a student would like to visit another maritime training facility and he would like to transfer modules from the one training center to the other. The trainer in the hosting facility has to assess the background of every student, and especially he has to assess the similarity of the content of the module for this case. So for this let's say task, we have identified three criteria: the C1, that is the workload in hours; the C2, that is the content similarity, where we have a scale: the more similar, the closer to 100, the less similar, closer to 0; and the C3, that is the level of higher education content. We can say, for example, that if it is 100, then it is only higher education level content. If it is 0, then it is exactly the opposite. So you can understand that there is a spectrum from 0 to 100 that signifies and illustrates, demonstrates the nature of the content. If it is, as I said, higher education, let's say 2 academic, then we expect a grade close to 100. So we have the three criteria, and then we compare them. As you can see, criterion C1 is always identical, is let's say equal to the criterion C1 here. That's why we have the 1 as a value in the matrix, because we expect, and this is what we say, that C1 is equally important with C1. The same applies for every single criterion here. As you can see, C2 is equal to C2 and C3 is equal to C3. This is a rule of thumb. When you have to check the matrix, you have to have a diagonal that is always equal to 0. The other point, as you can see here, is that we consider that C1 is less important than C2. In reality, what we write here is that C1 is 1/3 times C2. Or you can read the reciprocal value that C2 is 3 times more important than C1. As you can see, the values in the upper triangle here, 1/3, 1, and 5, have the reverse values in the lower triangle. Therefore, as you can see, if C1 is 1/3 of C2, then C2 is 3 times C1. And if C1 is equal to C3, then C3 equals to C1. So, given this input, what you see, this here is our input. Then we perform numerical calculations as per the theory and as per the instructions given in all the relevant papers. And what we derive is that we derive here a final ranking, a final weight of all these criteria. Please note the following. The theory gives us a threshold of error. This is the consistency ratio here. If this consistency ratio is less than 10%, then as per the theory, then we are satisfied with our input. If it is not, then we have to revisit our input. For example, C1 is 1/3 of the C2. What will happen if I say that C2 is less important? Assume that C1 is 3 times more important than C2. Do you see what is here the point? The consistency ratio is 83%. That means that our judgment is somehow wrong. Why? Because C1 is 3 times more important than C2. C1 is equally important with C3. However, C2, as you can see here, is 5 times more important than C3. So either this value here or this value here should change. Let's see what would happen if we change the value 5 here with the value 1. You still see that the consistency ratio is over 10%. That means that our judgment is not fully correct. What would happen if we use, let's say, 1/3 here? Oops, what a surprise. We have a consistency ratio of 0. That means that our judgment here is absolutely correct. So what you can see here is that we have, let's say, a perfect judgment. But let's use the values of the original judgment. C1 is 1/3 of C2, and C2 is 5 times more important than C3. At the end, what we get that the highest, the more significant criterion is criterion 2, because we have 1 here, and the other 2 criteria that have a relative weight of 0.281 and 0.237 is the C1 and C3 respectively. So we have derived the weights for the criteria, and then we move them, we use them here in the criteria weights. So as said before, the criteria, the weight for the criterion C1 is 0.19, the criterion C2 has 0.66, and C3 has 0.16. So assume that we have 3 modules, module A1, A2, and A3. And here we have the input. These yellow boxes here, the yellow cells, are input. So for example, for the C1 criterion, module A1 corresponds to 32 hours of workload, module A2 to 40 hours of workload, and module 3 to 32. While the content similarity, as per the judgment of the trainer, is 0.25, 0.8, 0.65 for every single module, while the academic content, let's say how academic vis-a-vis, let's say vocational, is the content, is graded as 0.8 for module A1, 0.65 for module A2, and 0.40 for module A3. This is our input. Of course, we can, let's say, see what will happen if we change that. Then we estimate the geometric norm, and we also estimate the normalized sum and the normalized product as per the theory. In this regard, we are going to use the weighted sum method and the weighted product method, 2 methods that we learn at school when we have to deal with multiple criteria. What we have done here practically is that for every module we have derived a value like 0.36, 0.366 for module 1, 0.711 for module A2, and 0.558 for module A3, and then we just see the ratio of A1 over A2. That signifies how important is A1 over A2. And the same we do for all other combinations, A1 over A2, A1 over A3, A2 over A3. This is the method that we apply for the weighted sum. So you can see that A2 is 1.2 times more important than A3. A1, 0.6 over A3, and 0.1 is 0.5 over A2. That means that this A2 module is, let's say, closer in terms of similarity. If we apply the weighted product method, that in this case is a little bit more correct mathematically, can one say, because we do not compare, as we have said, we do not rank, as said, we try to compare, then we get the values of 0.4, 0.5, and 1.2. As you can see, slight differences from the weighted sum method. What is the moral of the whole exercise? That we can see that A2 is, let's say, almost similar to A3, while A1 is, let's say, not very similar to A2 and A3. That is, all these results depend on our input. See, for example, what will happen if in the C2 criterion, that is, let's say, the content similarity, if we had a relatively low value, let's say 0.2. As you can see, A2 is not, let's say, the most similar module. It is, in this case, A1. So you see that A1, for whatever reason, this is, let's say, the numerical approach here, you can see that it is deemed numerically as more similar. We said before that the application of this technique is transparent. So you can see here in the original spreadsheet that every value here is practically determining the values and the results. So if we change 1/3 to 3 here as previously, we can see the relative weights as they change, but we can also see the consistency ratio. And that means that we can revisit every single step of our judgment of the methodology, and we can justify or we can reevaluate, reassess our judgment. And the same applies here, because given the input that we provide, we also get results. We have to be very clear. This is a very objective approach, and it is fully data-driven. Given the data that we have, we get also the results. The only element that quantifies our subjectivity is the so-called decision matrix here, where we actually say that criterion 1 is less important than C2, or it is equally important as C3. These three values here, 1/3, 1, and 5, reveal our subjective judgment, reveal our biases, reveal our priorities.